Warning: tube amplifiers have lethal voltages inside them. Please do not attempt to build, test, or repair these without understanding and following all safety protocols. Hey y'all! Well, we're back to work on this little Musical Paradise amp, and I'm not surprised that it got some kind of agitated folks in the comments. It does have a lot of hype train kind of going with this thing, and there's been forum posts and stuff, people raving about this, and I guess for a $300 amp, maybe this is what you get. I don't know, but I think it could be better. I know it can be. And went online, couldn't find a schematic, which is kind of surprising that in the 10 years this thing's been out there, or 15 years this thing's been sold, that nobody's gone through and kind of reverse engineered, the schematic. And I don't feel that this is some kind of proprietary information or some trade secret, because nobody in their right mind would copy this circuit. I mean, this amp just doesn't sound good. And so why would somebody want to duplicate it when it's simple enough to duplicate a good sounding circuit? And so I'm going to show y'all what this is. I'm going to show you some of the really goofy stuff that I found that just makes no sense at all to me. Had some folks saying, oh, well, you've just got a bad sample. The guy that mailed this to me's got 2 of these. And he said they sound the same. And I can't believe that, you're going to have 2 of them that are bad in the same household. And both channels are identical. And the voltages measure identical, and they measure what they should, and putting other tubes in it doesn't fix the problems that it has. Changing the circuit does. So that tells me that the parts like the output transformers and stuff aren't bad. So let's just dispel this whole notion that this is a faulty one. Just people try to do the same thing with the A12, the A50, the first R8 that I looked at, the R300. It's not because they're a bad sample. All those amps have problems. And we fixed them because that's what Skunkie Designs does. I take products like this, figure out what's wrong with them, and try to figure out simple solutions that you can implement on yours to get good audio on a budget. And so we're not going to go into the details of what I'm doing. This is going to be more technically oriented. I'm going to show you the schematic, how it's built. I'm going to show you some of the goofy stuff that's going on with it. I'm going to show you what I'm going to do. And it's not super complicated to implement what I'm doing. I know a couple of folks were like, oh, if we got to cut circuit traces, that's too much. I'm probably going to be cutting 2 circuit traces, and you just get a Dremel tool with a little cut-off saw. You can actually scrape it off with a screwdriver if you don't have a Dremel tool. So that's not rocket science. None of this is. And once I get the circuit design finalized, or the changes finalized, I'll post a final schematic, a BOM, and I'll do a how-to video on the other channel. We're going to leave one channel stock. We're going to modify the other channel so I can show you the differences as we go along. And I think you're going to see it's pretty dramatic. And I'm not going to give you a spoiler. You're going to have to watch the video. And here we go. So I wasn't able to find a schematic, so I had to draw one up. And I've also added the measured voltages. And this section in here is fairly kind of bog standard for a EL34 single-ended amp. Got the B plus that goes through the output transformer. There's the screen tap, or the ultralinear tap, some people call it. That's the plate lead, comes up here. One thing I don't like is this transformer's got more of a 20% tap than the more usual 40% tap that I'm used to. And so it does act more like a pentode rather than a ultralinear amp when it's got that low of a tap point, or it creates more distortion. But hey, that's what we're working with. And you can tell that because you can see how much higher the screen voltage is than the plate voltage. And we're going to do some stuff to address that. And then we got 23 volts on the cathode. This is the auto bias or the cathode resistor with the cathode bypass cap. One of the things that is a problem is this cap's too small. To bypass a 300 ohm resistor to get really good low frequency response, this needs to be more like a 220 UF minimum. And so we're going to pop a 220 UF cap in it and probably go with something around 100 volts because it doesn't need to be a 250 volt. There's only 23 volts across it. The other issue is they used a 200K grid leak resistor, which makes a low impedance for this coupling cap to work against, which also causes problems with low frequency response. And I don't think these two things themselves are the whole problem, but they're not helping anything. So we're going to also address that. And then this is the coupling cap between the two stages. So let's look at the front end wiring. And I think this is where the majority of the issues are. First, we got a 51K dropping resistor here to go to the front end or the driver tube. And as you can see, we lose over 100 volts of power on this one resistor. And I have no idea why this resistor is that big. It should be more like a 4.7K. The 33 UF cap's fine. This is the decoupling cap from the driver tube to the output tube. Has to be there to keep it from motorboating, and we're going to leave this alone. That's a perfectly fine value for that cap. So we come over here, power comes along this way, goes through this 100K resistor, and then it comes up here to the plate of the driver tube, and it's only got 65 volts on the plate. That's almost starvation levels of voltage for any tube. And I'm not sure why they've got this thing set up with such low plate voltage. And then the other thing that's even more bizarre is they're running this tube as a pentode, and they're powering the screen off this 200K resistor, and the screen voltage is twice the plate voltage. Never seen that in my life. The voltage should be at the max equal to the plate voltage, and in most cases when you're running a pentode in pentode mode like this is wired, it will be lower than this. So you would have, I would expect to see maybe 130 volts on the plate and 65 or 90 volts on the screen, and it's the inverse, which is like backwards from the way this is supposed to be working. They've got the cathode biased at 6 volts using this 2.7K resistor, and here's this 100 UF cap that all those mod forums tell you to remove, and all that's going to do is lower the input sensitivity. It's really not going to help anything as far as, the amp sounding nice and clean. And anyway, this is just a hot mess. And so let me show you what I wired up one of the channels like. So the changes or the added parts are in green. First thing we did is I put a 2.2K resistor into the screen of the output tube, and doing that lowered this voltage so it's about 5 volts below the plate, which is where I like to see it. And by doing that, it made the plate voltage higher than it was, which is a good thing. Got the same voltage here on the cathode. We put this 220 UF 50 volt, well actually the one I used was 100 volt, but a 50 volt cap is plenty for this position. You're never going to see over 25 volts on this point of the amp. Then we also dropped this from 51K to 4.7K, and now you can see we've only got a couple of volts drop from the B plus to the power going to the plate load resistor. For now, I left this 100K resistor in here. We're probably going to be changing this to a much lower one, but I wanted to be conservative to start with and not pull too much current to this tube until I did some measurements with it triode strapped. And by triode strapped, you remember there was all this, wiring here with a cap going over the ground and all that. That's all been removed, and we're just running the screen straight up to the plate of the driver tube with this 510 ohm resistor. If you remember, we had 65 volts here before. Now we got 155 volts. And I would really like to get this up closer to 175 volts. And we're likely going to do that by lowering the value of this resistor and then also lowering the value of this resistor. And I'd like to get this bias point closer to 3 volts. But for now, like I said, I just wanted to be conservative and run this tube really soft just to see what this did. And then the final thing we did is I installed a 300K resistor from the plate of the output tube to the plate of the driver tube. This is sometimes called a shade feedback resistor. It's a local negative feedback. It's not like global negative feedback. And you hear people saying, I want to make sure I get an amp with no negative feedback. This is not the kind of negative feedback that makes the amp sound sterile. This doesn't do that. This helps lower the distortion without causing those kind of issues that global negative feedback can cause. So, again, we've got good plate voltage here. We've triode strapped this tube. We've gotten rid of that weird problem where the screen voltage was super high compared to the plate. And we're going to be doing another round of this. This isn't dialed in at all. But I wanted to do some testing and see if triode strapping this tube along with fixing this grid leak resistor, you can see we raised it to 510K so that it isn't causing an issue with this 0.22 UF coupling cap. And then along with this change and dropping this screen voltage, I wanted to see if that was what was causing the super weak low frequency response. So again, this is not the final schematic. So do not go into your amp and put this stuff in it. I mean, this stuff over here is likely not going to change at all. And this could change. This resistor can be varied from 200K to, I've run them as high as 1 meg to tune the way the amp sounds or to change sonically the balance of the tone. But 300K is a good starting point. And again, we're going to be changing this. Likely going to be going to a LED resistor bias like I've done in a lot of my amps instead of using this resistor and capacitor. But that's for another video. Let me show you what these changes did on the audio analyzer suite. Okay, so what we've done is one side of the amp is stock and the other one's got Skunkie mods on it. And again, understand that I haven't started really dialing in the bias point or the plate load on the driver tube yet. I think we're probably about 25% of where it should be. So dialing that in should help the distortion. But let me show you what we've got going on in this early stage, because I wanted to see if this was going to fix the problems that we were seeing. So here again is a quick run of the stock side, or the way it comes out of the box. And this is with EL34 output tube and the little red metal RCA driver tubes. And like I talked about earlier, you really can't run those 6L6 GTs because you'd be running them at about 115% and they just would not last very long. And these EL34s are running about 90% the way they're set up right now. So as you can see, at 1 watt, we've got 1.5% distortion. We've got a little over 2% distortion. And then at 3 watts, 2.5. And at 4 watts, we got 3% distortion. And then right along in here is where it starts clipping. I think we were able to get 6 watts out of it. So let's go ahead and flip to the other channel real quick, and let me show you what this screen looks like now. And now you can see 1 watt, we've got 1% distortion. At 2 watts, we're at a little over 1.5. 3 watts, we're at about 2.25, 2.3. And at 4 watts, we're at 3% distortion. And I'm hoping when I get the input tube bias nailed down, not only will we see a little less distortion in here, maybe not a lot, but probably another 0.5% can be toned out of here. And then this input sensitivity can be increased a little bit, but it's still not bad. At 1 volt RMS, it's making 4 watts. And then at peak power, which is probably around 6 watts, you got 1.2 volts RMS, and any modern source should be capable of 2 volts RMS. So let's come over here and run the frequency response curve again, and this is on the unmodified channel. So as you can see, as you get down here, even at 1K, it starts rolling off, and then at 100 hertz, it just falls off a cliff. And by the time you get down here to 20 hertz, it's 7 dB down, and if we try to hunt the -3 dB, it's around right at 40 hertz, which is what we saw last time. So now we're going to switch channels, and let me show you what it looks like now that we've done some corrections to the circuit. So now this part of the curve looks, it's actually flat down to about 200 hertz. I mean, the difference between here and there is about 1/4 dB. And then when we get down to 40 hertz, we're only down 1 dB now. And now the -3 dB point is around 16 to 18 hertz, which is a huge difference. This is going to be definitely audible. And again, I don't have the driver tube dialed in yet. I'm not sure if that'll impact the frequency response, but it could. And then here on the top end, we definitely have less roll off as well. At 20K, we're only down less than 0.5 dB. And so, massive increase in frequency response from these circuit changes. So the next thing I want to do is show you the THD versus frequency. So let me switch it back over to the original circuit. So here we go on the unmodified channel. So you can see down here in these lower ranges, we have a ton of distortion. Even down at 100 hertz, we got over 6% distortion. And this is being tested at 2 watts. So if we turn this up, it'll be even worse. And then like in this range in here, you know, even down here at 300 hertz, 400 hertz, we're 2.5% distortion, and it really doesn't get down into a reasonable range until over 1K. So let's flip it over to the other channel and see what we've got after we've modified the circuit. So you can see in this range here where it was like 6% before, it's under 2% or close to it. And then, you know, down here at 20 hertz, we still got some pretty high distortion. And I think what we're seeing in this slope here is a function of the output transformer. But what we were seeing on the other screen in this range here was that the circuit's all whacked out, and we're starting to get this sorted out. The last thing I want to show you is the square wave, and we got a little bit of ringing still, which I've learned makes the amp sound fairly lively. Doesn't bother me. I mean, as long as it stops and it doesn't just keep ringing all the way across, which would mean that the amp's unstable, it doesn't bother me at all. But see how nice and almost flat this line is? And then here's the square wave on the other channel, and you can see how this is much more sloped than it was on the other screen. But then this one isn't as sloped, so we've got like asymmetrical kind of clipping going on. And then if we look at the, let's look at the 100 hertz square wave just for fun. Yeah, that's not very pretty. Got a massive slope in it. And let's see what the other channel looks like at 100 hertz now. Definitely a lot smoother. So we're definitely moving in the right direction. And yeah, we're not totally there yet. I still need to sit down and I'll show you calculating up on the load lines. I don't have load lines for a triode strapped 6SJ7, but I've got one for a 6EJ7. So we can calculate up what that's going to look like going off of that tube's load lines, triode strapped. And it's probably going to be some trial and error finding the right cathode resistor. Might be easier to do my LED bias trick, and that should also help with the distortion. So anyway, I think it's a good place to wrap up this video. And as you can see, we're heading in the right direction. We got a huge improvement in the frequency response curve, and while this thing may not be a bass monster, it's not going to sound like the bass track was deleted. And I think that super funky 65 volts on the plate and 130 volts on the screen is probably what was causing some of that funky distortion that was creating like that echo reverb kazoo sound that I was hearing. And also getting the screen voltage down on these EL34 tubes, which makes the plate voltage go up. It's going to make the amp sound smoother, have sweeter mid-range, and just, to me, makes the EL34 tube sing. Also, you could see, and I didn't really show this, but these tubes are being run about 90% dissipation, which is a good thing. But do not run 6L6G or 6L6GT, those 19 watt tubes. Do not run them in this amp. They'll be biased at like 115%, and it's going to end up killing them. And so, EL34s are fine, KT66s, KT77s, any of those 25 watt tubes are what you want to be running in this thing. I wouldn't run KT88s or 120s are probably going to cook the transformer from the heater current, so I would not put KT120s in this. But even KT88s, you're just going to be running a really high heater amperage for no benefit. So I would stick with these 25 watt tubes. So anyway, still got some work to do on getting the bias point for the driver tubes finalized. They're biased really cold right now, which is still going to work much, much, much better than trying to run it as that goofy Pinto thing that it was. But I think it could be even better by biasing these things up. Probably going to do the little LED resistor combo thing like I did on my KT120 monoblocks, but we'll see. Shouldn't be too hard to implement that, and I do think that sounds really good in these kind of amps. Probably going to give the option of using a specific resistor capacitor, but then you got to replace that capacitor that's on the board instead of just getting rid of it. And I know a lot of you guys have already just clipped and thrown away that capacitor. Then you got to clean out the solder holes and all that, so we may not get into that. So anyway, yeah, this thing looks like it can be fixed fairly easily. The output transformers don't appear to be a major roadblock to getting decent performance out of this. I still think the best upgrade to this is going to be putting some EdCore open frame output transformers in it. And again, 120 bucks, something like that, shipped for a pair of them. I think they're $47 plus shipping. That's, I think, a good investment. People are spending way more than that on fancy tubes for this, and instead of buying some Muller EL34, $200 a pair tubes, let's put some better iron in it and just use some JJEL34Ls. And again, once I get the front end biased up where it should be, these little red RCAs may not be what we end up using. Could be the Sylvanias, could be some other thing, I don't know. Definitely going to be the 6 SJ7s. Those 6 SD7s are remote cutoff pentodes. Those should not be used in audio. The sharp cutoff pentodes can be triode strapped and sound really good in an audio amp. So anyway, hope you're enjoying this content. Probably going to have one more video where I'm going to go through drawing the load lines for the driver tube, kind of figuring out how to set the cathode bias up and the plate load resistor and all that. Be kind of a learning experience for you guys. If anybody knows where some triode curves for a 6SJ7 or this, what is this RCA? It's a 5693. Not the pentode curves of the data sheet. Of course, I can find that, but somebody that has triode curves for these. That would be super helpful. If not, I'm going to assume a 6EJ7 is very similar, and we'll experiment from there. So, again, hope you're enjoying this content. If you are, please subscribe. Please like the video. Thanks to you supporters that support me on Patreon. And until the next video, have a nice day.